Good morning. Welcome to GDC 2017. Thank you for getting up on Monday morning and coming to see us. This is the Math for Game Programmers tutorial. We're going to be doing sessions throughout the day on various topics in math in games, so feel free to join for whichever sessions you like. I'm supposed to ask you and remind you, please silence your phones or your pagers if you're a drug dealer. At the end of the session, if you haven't been to GDC before, or if you have, it's good to be reminded, you'll be getting an email that asks you to review the session. Please do the review. It just takes a second, and we really appreciate and read the feedback that you give. So today's schedule, we're going to be doing 2 one-hour talks this morning, starting with myself and then Mike Acton, and then we're going to break for lunch, and then we're going to have a number of half-hour talks in the afternoon. And we'll have this schedule up as we go. Okay, so first, I just want to get a sense of who's in the room. So please raise your hand if this is your first GDC ever. Awesome. That's about half, 2/3 of the room. And then put those hands back up, please. And also, if you've been to GDC but you've never been to this tutorial before. Okay, so that's mostly first-timers. Please raise your hand if you're a student. Only a few. An educator, a couple as well. Or if you work in games full-time. Okay, the vast majority of the room. Okay, so my talk is based random generation. More like why be random when you can be noisy, or I'm going to make a claim that anything random can do, noise can do better. I'm a game designer programmer. I've been coding since the Apple II. My background's in physics. I've been doing this professionally for a long time, and I present regularly at the GDC, and I teach now at SMU Guildhall, which is a grad school for game development. I've worked at a bunch of companies. I was a tech director or lead programmer at each of those companies, and I've worked with a bunch of companies on a bunch of projects. So today, we're talking about number generators, right? From RAND to whatever else. We're going to talk about some noise functions, and I'm going to get into that a little bit. Just a couple of brief versions of smoothed or fractal noise, like Perlin noise or simplex noise. I'm going to make a case that I think noise is more valuable in some cases than random, or can even supersede random. And then we'll, of course, try to give some application and context for all this stuff. So the talk is for anyone who's interested in procedural content generation. That's been a hot topic lately. Of course, anyone who's just rolling dice for random outcomes in general. If you're using RAND, this talk is definitely for you. Even if you're using the Mersenne Twister or something you think is more sophisticated, this talk is for you. Or if you're doing any sort of noise or hash functions and you're using something like MD5 or SHA or something you found on Stack Overflow, this is definitely a talk for you. Okay, so some example use cases just to frame what is this, because everything context is king, right? Depends on what we're doing. So one of the most popular things we're going to use random numbers for and noise is for generating procedural worlds, right? And everyone thinks about, height maps generating mountains and lakes, and yes, we can do that. Or generating random dungeons for roguelikes or something, yes, we can do that. There's a lot more we can generate though, right? We might generate planets or villages, spaceships, flowers, random NPCs with random genders and personalities and backgrounds and professions, random quests, right? So there's a lot of other things we might want to do with generation other than just mountains. There's some harder problems that are more nuanced too, and Shay Pierce is going to talk about this a little bit this afternoon, where we might want to create discrete and distinct things in a near infinite world. Or we may want to place objects in a really large world, right? And so, for example, in Minecraft, you can run forever, but every now and then there are periodic trees or periodic villages. And how do we decide where to place those if we can't figure out where to place them all at the time because the world is infinite, right? So we need to do all this kind of on the fly. We might want to do particle effects. We might have 1 million particles, each one doing a random thing. That can get really weird if we're doing it badly. There are a lot of AI algorithms nowadays that require randomness, whether it's Markov chains, genetic algorithms, Monte Carlo search. And again, going back to the Minecraft example, we might want to have chunks that generate in random order, right? So if the player runs to the west, he discovers a mountain. Great, there's a mountain there. He then only sees half of the mountain, so only half of the mountain's been generated. He then runs away from it, goes south, comes all the way back around, and approaches the mountain from the other side. The mountain better still be there, and the west side better match up with the east side. We may want to trade seeds, right? I may want to tell my friend, hey, you should try this map. Try this seed from this word or this number. It's a really cool map. It's got a tower in the middle of the jungle, something like that. Generation and noise can also be the ultimate form of network compression, right? If I have 22 gigs of data that I generated, I can send it to you with an almost infinite to one compression if I just send you the feed, right? So that's a huge advantage. That's the same with disk compression, right? If I generate some mountain, as long as the mountain's unchanged, I don't need to save it on disk. I can just throw it away and regenerate it on demand. So it's the ultimate form of compression as well. All right, so briefly, I want to talk about, well, what do we actually want out of our number generators? Which ones should we actually use or not use? We keep hearing different things. A couple of the limitations of random number generators. I'm going to talk about noise functions as an alternative and entertain the possibility of can we make a random number generator that's based on noise or noise that's based on random number generators, and then a couple of tidbits. So that's where we're going to go with this. So first of all, what do we want to look for in a random number generator? What makes one good? Well, I think academics would start answering, well, it depends on the period of the blah, blah, blah. No, it really depends who's asking, right? If you're at the NSA, you have very different needs for your random algorithms than if you're working on Minecraft, than if you're working at a casino game, right? So it really depends who's asking. So what do I want in an RNG as a game developer who's interested in procedural content generation? Do I want fair statistical distribution, right? It's random enough. Yes, I very much want that. And 99% fair and statistical is much better and more important than 95% fair. It doesn't have to be absolutely perfect, but we really start noticing the differences with fall off. We want it to not repeat, right? If we're flipping heads, tails, tails, heads, 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 we don't want that to happen. Except actually, we do in the sense that it can and will happen, and so we want it to happen as much as it should, right? Do we want some really long repeat period where if we run the random number generator, it will only finish its cycle after the sun has long burned out and died? That's really important, right? Probably that doesn't matter so much. As long as it can go, billions or something, really who cares at some point? I'm going to make this point in a different way later. However, we probably do want to make sure that it doesn't repeat too quickly. So as long as we can get millions, billions out of the sequence, we're probably in the ballpark of okay. And most of the random number generators you'll deal with have a sequence length, a period of in the billions, so probably not a big deal. We want to be able to seed it, right? We want to be able to say, I'm going to give you the seed of 15, and then go, 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 generate a world. And that's totally different than if I give it a 17 and I said, generate the world. So we want to be able to seed it. And I want to be able to use more than just a few seeds. So maybe 32-bit, that would give me 4 billion seeds. That's plenty, right? There's a lot of random number generators that have pickiness about its seeds. Like, use any seed you want. Oh, except don't use even numbers. Please use large primes. And definitely don't use 0. So I'd rather not have that if I can avoid it. Some RNGs have this sort of warm-up period where you get some lousy values before you start getting really good values. And actually, some of the most well-known generators are some of the worst at this. This is not something that I want because oftentimes I'm going to want to seed something and then generate 5 numbers and seed something else and generate 20. So it's those numbers at the beginning of the sequence that I want the most. So I don't want this warm-up. Statistically, it is important for me that the bits are independent, right? If you give me 32 random bits, then there should be a 50% chance that any one of them is on or off at any time, and a 50% chance that any one of them agrees or disagrees at any time, right? They shouldn't be correlated with each other spatially, and then temporally, meaning that the next result and the next result shouldn't have anything to do with the previous result, at least not recognizably. Platform independence, I definitely want this. If I have an Android client and an iOS client, and a Mac and a PC client all connect to something, and they're trading seeds over the network, that thing I generate from the seed you sent me better be the same as this thing you sent, even though you have a totally different CPU than me, right? You might be on a 32-bit ARM or whatever, and I might be on a 64-bit Intel, right? It could be quite different. I would love to have order independence, random access, right? Where I could just sort of jump ahead in the sequence and jump behind. I want to say, give me the 75th random number in this sequence. Unfortunately, that's something random number generators do not do very well. We'll talk about that more. And then, of course, I need this reproducibility, this determinism, right? If I give you the seed 17, I better get the same results as the next time I give you the seed 17. And this is crucial to most of the purposes we're going to do with this. How important is speed? We may end up wanting to generate a lot of random numbers, like a lot, and we may want to do it in real time. Some of the most interesting algorithms we can do require us to generate millions of random numbers. So this does matter. And we also may want to have thousands or tens of thousands of random number generators that we're going to instantiate, that each one is feeding us different numbers. So we may also care about the ability to whip up another generator and have it start cranking out numbers. Memory footprint, how much memory does each RNG have? If I've got 10,000 of them, am I going to care? Am I going to notice? Is that going to be megs and megs of memory or not? Can I run it in parallel? Right? If I have multiple threads, can they all be rolling random numbers at the same time? Is this thread safe? Can I use one RNG, one generator, that multiple threads are saying, hey, give me numbers, or does each thread have to create its own generator, which is not the end of the world? Okay, so which RNGs are out there? What can we use? I'm going to go really quickly through this, but just a sense of what kinds of things there are. So the simplest random number generators, like these, are literally boiled down to, if you can see the code on the bottom here, some internal state, say some number, and we multiply it by some weird number, say a big prime, and then that's our new state. Oh, and then we return it to you. And then the next time you call it, we take that new state and we munge it some more, and then we return it to you. So we kind of are constantly chewing and mangling our state and returning it. This sucks because if I put in a seed of 0, meaning I start the state off as 0, then it will be 0 times I don't care, because 0 is 0, and then it will just be stuck at 0 forever, right? In the numerical recipes, they improve this, and these are called mixed congruential generators, where they just multiply by something and add a number. Great. And supposedly this, I thought, was what RAND was, but my results later in this tell me that it's doing something even more sinister. Okay, so that's great. Why not just use RAND? It's been in the standard forever. Everyone knows how to use it. Well, probably you know that RAND only gives you so many numbers, right? 0 to 32,000. Okay, well, if I wanted a 32-bit RAND, I'll just mash 3 RANDs together, right? Maybe bit shift. So I could make something called triple RAND, right? Where I take these, see if you can see my mouse cursor, these 15 bits that it's giving me, and actually the bottom 2 bits are a little bit statistically wonky, no problem. We'll just generate RAND, shift it over from some bits, generate RAND, shift it over, and then mash those together. Now we get 32 good bits of random. Unfortunately, RAND's not that fast when we start doing millions and millions of calls, and of course it's not going to get any better if we call it 3 times just to try to get better results. And RAND does not do well at all statistically in terms of how evenly distributed the random numbers are, though this triple RAND can do fine. Also, random maintains a global state. So if I have 16 different threads, I can say sRAND to seed it to the number 17, and then I call RAND, RAND, RAND. If some other thread is doing that as well, it's fighting with me and it's disrupting my sequence, right? So it's absolutely the worst thing for me to have in terms of multi-threading. And that's just the beginning of RAND's problems. So let's look at a couple of sort of quantitative grades of how well these things do and how fast they are. So identity here is a random number generator where every time you say, give me another number, it says, okay, 1, 2, 3, 4, 5. That's all it is. So obviously that doesn't do very well. And I have these different tests, and we could talk about them later if there's time, but on average, are the bits 50% on or off? On average, are bits independent from each other? Is the next number more likely to be higher? That should be true 50% of the time. When I look at each byte, are the bytes distributed over the different possibilities nicely? And then if I mod by all the different numbers from 1 to 1,000,000 and do that a ton of times, does it statistically mod, spread nicely? So if I do this rand mod 7, do I tend to get about even results across those 7 buckets? And you can see here these early and common random number generators, most of them do not do well at all on these statistical tests. This triple rand does much better, thankfully. If we look at the call time, this is the top here, you can see I can make quite a number of calls per millisecond, but triple rand is down to 10,000 calls per millisecond, which seems pretty fast, unless, again, we're going to be doing millions of them. So not bad. I would say you're fired for all of them except for this triple rand so far. Okay, there's some other ones to consider. I'm not going to go into too much detail, but if you have to leave in this talk right now, I would say the one takeaway is at least use something like this XOR shift 1. It's like rand that doesn't suck. And it's a simple algorithm where you just sort of bit shift around and XOR with yourself. And you do that enough times. Surprisingly, it has very good statistical results, and there's various other variations of it. Now, by now, probably many of you are thinking, well, geez, why don't you just get with the program? We all know there's Mersenne Twister, and that's the best thing, right? And it's in the C++ standard now. Let's take a look. First of all, it's not simple, right? If I call rand on the right, it does a bunch of stuff, and one of those things is every now and then it calls twist, which is a bunch of stuff on the left with a for loop, right? Branches. This just doesn't smell that fast to me, and sure enough, it's not. We'll go more into that in a second. Here's another one that's, Intel actually has some really cool random number generators on their website. This is one I took from their website. Everyone can obviously understand this code, right? So you all see what's going on there. So let's look at how these do. When I look at these different random number generators, you can see now everything triple rand and below is scoring pretty well. Mersenne Twister actually only scores a 98. There's another set of tests you can apply to these, which I'll talk about at the end if there's time. But these are more simple and direct to what I wanted. So actually, Mersenne Twister was not the strongest. These XOR shifts were slightly better. And if you look at the time to run them, Mersenne Twister's pretty fast, but the XOR shifts are better quality and they're faster. All right, so that's interesting. There's another thing that's interesting here to note is Mersenne Twister. Notice it takes, to seed it, it's hundreds of times slower than any other thing. It's so complicated to seed the structure, and it's also got a lot of memory. Okay, all of these functions are based on the central idea of a recurrence relation function. And that's basically just to say, any RNG, just pick one. It basically amounts to this. Take your state, do something funky to it, and return that. And then that's your state for next time. And then you do something funky to that. And so as long as you pick the right funky, this thing will create a long chain of interesting things, hopefully. Okay, so lastly, I'll just mention there's STD random device. It's a new thing. I don't know if it was C++11 or something they added. This is something you should not use for your random number generation. This is meant to be physically, actually, really random, right? Like, I don't know if it's based on the temperature of the core or something like that. I don't know how you do that on a computer. But it's meant to be an actual random, not a pseudo-random. For games, that's not really useful at all, unless perhaps you want something super randomy just to kick off your random number generator. Okay, so I want to talk about the limitations of these random number generators, all of the ones we just discussed. Many of them have restrictions on the seeds. Like I said, if you use a seed of an even number or seed them with 0, half of them break right out the gate. And a lot of them have even weirder rules, like you should use a seed that's a prime, or a seed that's a prime that's 1 less than a power of 2, or something like that. That's no use for me if I want to have different planets with ID numbers or NPCs with ID numbers, and this NPC is ID number 12. Please generate yourself based on that seed, right? Well, what if that seed doesn't play well with the random number generator? Am I just going to get a really lame NPC, or I'm going to get a lot of clones of the same NPC? There's a bigger complaint I have, which is that when we say seeds in these random number generators, I think it's kind of misleading. They're not really giving us a whole new set of random numbers. They're just jumping us into a different starting point in that same sequence, right? So if the sequence is 1 billion numbers long, we might start halfway into it if we use one seed. We might start a third of the way into it if we use a different seed. And this is why the mathematicians get us all excited about something like Mersenne Twister having a ridiculously long sequence, a period before it repeats. Is because when you sort of jump into it, you're not likely to sort of find familiar territory that you were in before, hopefully. But the seeds are not really a different set of random numbers. They're just a different starting point. I mentioned the slow warm-up, right? Mersenne Twister included, produces weak values before it starts getting statistically strong. And that's fine if you're doing scientific programming. You want to have 250 million random results, and you want them to be statistically sound. It's not fine if you want to just make an NPC and you need 6 die rolls and they're all bad. Thread safety is important. Something like Mersenne Twister, and most of them, uses an internal state, so it's not thread safe. Every call to it modifies the random number generator. However, you can instantiate a different generator on each thread, and then each thread can hammer on its own generator, no problem. However, you can still have the case where this thread seeds with the number 5, this thread seeds with the number 7, and this thread is pulling numbers, and this one faster than this other one. And actually, because we're still all pulling out of the same sequence of numbers, we can kind of sort of sync up. And so I can pass you or lap you or even come in sync with you in the same part of the number sequence. And of course, RAND, we said, do not use across threads because it has this global state. Order dependency. This is my single biggest objection to these random number generators. Every call affects the next one, so whatever you generate has to be generated in a strict order. If I give you the seed 17, that's not enough. You have to generate the same NPCs, tiles, maps, weapons, loot, drop, whatever, particles, in exactly the same order that I did, or else the sequence gets disrupted, right? So it's very sequential. It's highly ordered. This sucks when, say, we want to generate infinite number of things out of order. So just to illustrate that point, so let's say I have some world that's an infinite world, right? And I can go as far as I want, and the world just keeps generating over and over and over and over. Well, if I see that there's an island over here, let me get some island. Okay, so I don't know if you can see in the distance, there's an island that's kind of half generated. And I'm going to back away from it, and then I'm going to go around here. And now I had to go exploring. I'm going faster than the thing can catch up at the moment. But if I then approach from the east instead of from the south, I still have to come up with that same island that I would have before, right? So I can't roll a bunch of random numbers ahead of time and just figure out where all the islands are, because there's an infinite number of them. And I need to be able to encounter them in random order. So we have poor random access. How do you jump 100 numbers ahead in the sequence? In any normal, traditional random number generator, you just have to roll 100 times, right, to skip ahead for some reason if you needed to do that. You want to jump back 3 in the sequence? Sorry, can't do it. Maybe if you knew, oh, I was generated from seed 2261 and I'm 1,400 calls in, you could reseed and then call 1,397, right? That's ridiculous. So we have terrible random access. We also have non-trivial instantiation. Like I said, there's a lot of interesting algorithms that happen in procedural generation that require us to have thousands or tens of thousands or even hundreds of thousands of different random number generators instantiated. So if we can't make them fast and if they're not small in memory, that actually takes tons of tools away from us, takes tons of algorithmic, interesting procedural content options off the table. And then there's the lack of temporal and spatial coherence. And by that I just mean if you want to have a slope that's random heights and you're kind of smoothing it out between them, you have to generate the numbers ahead of time and remember them in order to smooth between them, right? You can't go back and say, wait, what was the number before? Too late. So it means you have to end up writing all this extra code and storing all this extra data. And if you're still really, really jonesing on Mersenne Twister, I'll just quote Wikipedia. Places a load on memory caches, somewhat slow, fails tests, not appropriate for Monte Carlo simulations, outputs nearly the same sequence for many iterations. All right, so I'm not saying Mersenne Twister is bad. I'm saying when you talk to anyone on the street, a game developer, you ask them what do they know about random numbers, they'll say, oh, rand is bad, you should use Mersenne Twister. That's the one thing they know. And I'm saying that's not necessarily true. It's heavyweight. Every RNG you instantiate is 2K of memory, which I still can't believe. It's slow to instantiate, I'm sure, in part because of mucking around in all that memory. It has a lumpy cost amortization, right? We said we roll a random number, and then every now and then it has to say, hold on a sec, and then go spin up a whole another batch of numbers for us, right? So the times are even inconsistent. It's got these cold starts where it gives us crappy numbers at first. It's strictly sequential. It's got sensitive seeds, right? Don't put a 0 in the seed. Don't put some other numbers in there. Even just seeds with a lot of zeros in the bits can confound it. And it's super cache unfriendly. When you're mucking around this 2K of memory and your cache lines are 64 bytes, you're going to be not going to be cache hot, even for something as simple as a random number generation call. But at least its quality is amazing, right? Okay, not so much. So let's look at noise functions and compare them. So a noise function, what I mean by that is like an infinite table with a bunch of numbers in it, right? I put in the number 7, and I get out the number 0.09. And then if I put in the number 4, I get this. If I put in a 7 again, I will again get 0.09. So it's just a lookup table, effectively. But since it's a function, it's just math, it's like an infinitely large table that takes 0 bytes, other than the code. And basically, these work all more or less like this. We put in a position, the number 7, it mangles the bits around, mashes, and returns something that's random. But it was based on that 7. It started with those bits, so it's always going to give the same result. So all these noise functions are basically the same in the sense that they take what you give them and they mash it up. Great. It has 0 state, so we can instantiate millions of them, no problem. In fact, we don't even have to instantiate them. They're functions, right? We just call them. There's no recurrence relation. It's not taking a state and eating itself, and then that's the next state, right? There's no leftover state, which means it's totally thread safe. You can call it from 1,000 threads all at once. No one's bothered by it at all. And now we have true random access, right? You want to jump forward? No problem. Just ask what's at 107 in the table. You want to jump back 3? Just ask what's at slot 4. You can ask any slot, any time, any order. No problem. Lastly, we can integrate true seeds into this, where it's not just the same sequence and we're like kind of looking at a different part of the table. Each seed can give us a totally different set of an infinite, near infinite set of numbers. Okay. Whoops. So we can also do 2-dimensional noise, 3-dimensional noise, and the same idea is the same. The basic idea is the same. Imagine, again, an infinite or near infinite table of x and y, and I can plug in any x and y, like 2, 0, and I'll get a 0.05. Or I can plug in a 0, 2 and get a different number. So I want a different number for every xy combination, more or less, and I always want the same number for the same xy. So again, it's like an infinite 2-dimensional table for no bytes. Unfortunately, noise is only good for certain things, right? We don't use it for very much. Maybe if we had an RPG and we have different grass tiles, we might have the position of the tile look up into noise to say, oh, I'm grass tile number 3 or I'm grass tile number 2. Yeah, that's nice. If you've used Perlin noise, you'll know that a noise function is the basis of that, so we have to have one for that. And that's usually all people use these things for. We can do more. So First of all, like the grass example, we can use noise to make things more organic, right? If you have 10,000 orcs, if each orc uses noise based on his own unique ID to determine, is he a little bit more slouched, are his forearms stretched, is his skin a little bit redder, are his teeth a little bit longer? Now you have an army of all orcs, all different, right? Even if I have this, say this grass here, I love this picture from Chris Berkey. If I just apply some noise to it, it looks organic, right? Just mild, moderate, small variations. That's totally predictable. Okay, fortunately, because we can skip ahead and behind and anywhere in the sequence, this is super useful for generating world chunks, planets, villages, NPCs. And we can generate them in any order. It doesn't matter whether the player in your RPG goes to this village first and talks to these people, and then this other village second, and we generate them on demand. The result will be the same if he goes to the villages in the opposite order, because each village is not generated from a sequence, but from these noise functions. So it also means that if we want to know where things are going to be, no need to generate everything up front. We can always generate the numbers on demand, and they're always going to be consistent, right? And because we can generate them in any order, that means in X order or in Y order. That's a really hard problem for RNGs. And there's no need to store massive amounts of data. We can always just reproduce it. In fact, your computer just keeps getting faster and faster and faster, and memory is not keeping up. So in many cases, it's faster to compute something than it is even to look it up nowadays, especially if the lookup tables are really big. So don't be afraid of letting the CPU do a little work. And it's also really useful for placing scattered objects within an infinite space. And this is a very hard problem, but it's one that you're going to encounter if you do a lot of procedural generation. So let me give you an example of that. Here is, I don't know if you can see that, a random function, right? I'm just showing a bunch of different random values. And if you're familiar with Perlin noise, which we've done talks on in the past, Perlin noise is like a fancier version of this, which takes, let me do it like that. It takes a simple smoothed function that's based on it's going up slope or down slope based on some random noise, and it layers noise upon noise upon noise, and you get these really interesting sort of crunchy, cool results. Okay, so if we have this, and this is an infinite landscape, right? This goes on forever, much like Minecraft. So now let's say I need to place things throughout the landscape, like I need trees every so often. I need villages every so often. Well, one of the best ways you can do that is if you're using a noise function, or especially a smooth noise function, you can look for wherever there's a local maxima, like a peak of a mountain. Can everyone see those blue stripes? So if I zoom out a little bit, you can see there's going to be mountains pretty regularly here, but as I increase the noisiness of the noise, I'm going to get more peaks, right? Now I have kind of a double peak at the top of that mountain. And so I can easily say I want to have fewer trees, I want to have more trees, I want to have trees that are moderately spaced. And I can even say, oh, you're going along, there are scant trees in the plains, but as you get into the foresty areas, I'm going to slowly increase the tree density knob, and we're just going to get more trees. And this is infinite trees, mathematically predestined from no matter which way you go, we just know where they're going to be. And we can ask any piece of the world, where are the trees, where are the villages? So this local maxima trick is really nice. Again, only really works with noise, but you can still do it with, let me go here. Even with flat noise, right, just like this, we could still decide to say, hey, there's a tree anywhere where the noise value of, where some square's noise value is higher than all of the guys around it. So this would be a tree, and this could be a tree, and this could be a tree. And that algorithm, again, works even better if we've got smooth noise, like Perlin noise. And we can just locate the local maxima, right? So all the mountaintops here I can highlight. So I can make the noise as crunchy or as smooth as I like to get more dense forest or less dense forest. And this just goes on forever, right? So I can use this local maxima with trick, which is really nice. And it works even better with smooth noise. It's easy to adjust the density, so you can say there's a lot of treasure chests spawning in this area. And we have real seeds. We're not just jumping to a different place in a sequence. If I give you a seed 17, you have a totally different infinite table of numbers you're pulling from than my infinite table of numbers I'm pulling from. Which totally eliminates that problem of, oh, I might catch up with you just through bad luck in the sequence. Okay, so let's now try to relate RNGs and noise and see how are they the same and how are they different. Okay, so pretty much all RNGs look like this top thing. It's a thing that has state. You say, give me another number. I'm calling that function rand. And it mangles its internal state and returns that to you. More or less, this is what basically all of those random number generators do. The noise function is almost the same, but the difference is subtle. There is no state, there's no class, there's no object. Right? We just pass in a position, and then we do that same funkiness, but then we just return it right away. That's really the only difference. Nothing mystical here, right? So, can we build random number generators if we do want numbers in sequence that are based on noise? Could we build a noise function? Could we build a noise function out of random number generators? That's what I'm asking first. So this is kind of like pretending something that you're not to be something you're not. So here is a random number generator, and it does exactly what I said, right? It does funkifies its state and then returns the state to you. I can make a noise function out of this. It's a little ghetto, but I can basically say, okay, hold on. I'll construct a random number generator, and I'll seed it with that position you gave me, and then I'll return the first number in the sequence from that seed. This totally works. So using this, you could use rand, or Mersenne Twister, or XOR shift to generate those Minecraft worlds. It's not fast, right? You're constructing these things all the time. And if you don't want to construct it, you could make this be like a local static or something, but now you've ruined it. Now there's state that's lingering. And it's not a strict noise function. So yes, we can do that, but it's not pretty. And it's not fast, right? We have to pay for the construction, the initialization, the seeding, as well as the rand itself of whatever RNG we used. And we said for something like Mersenne Twister, that's not fast at all. Okay, can we go the other way around? Can we make RNGs that are based on noise? So again, we're kind of pretending to be something we're not. Let's see how it goes. So this is now a thing. It's a class, an object. It's an RNG, and this is going to be my special RNG I made that's based on noise. Let's say that it has one piece of state, which is the current position into the noise. And we'll say that starts off at 0, and then it has a function rand. And what does rand do? It just says, do something funky based on my position, and then advance. So basically, this is just like you're looking at the table, that infinite table from the noise, and you just say, give me another random number, give me another random number, give me another random number, and it's just surfing down the table. No problem. And actually, that's pretty fast and tiny, and it won't repeat, right? Because it's not munging itself, it can't get into some weird cycle where 0 begets 0 or anything like that. Or even 1 begets 7, begets 2, begets 1, begets 7, begets 2. Because it's based on this ever-increasing position, it's extremely unlikely to be cyclic, since it's not based on this self-munging function, right? Okay, it's tiny, it's fast. How tiny? How fast? Like, it's not faster than an actual RNG, right? Well, obviously, that would depend on the noise function. So let's go back to noise functions. I want to give you a couple of examples. So if I have some noise function, I'm going to say for this talk, I'm going to frame them all like this. You put in a position, and you get out some mangled random bits, like you looked it up in that imaginary table. So there's a lot of ways you can do this. One way is to multiply by some big prime number. Why prime? Well, if we multiply by 12, then I know that the result will be a multiple of 3 and 4, right? If I multiply by 2, or any even number, then I'm guaranteed to only get even numbers out. So generally, we want to only multiply by prime numbers. We like big prime numbers because they're going to just mash all the bits. There's going to be crazy carries everywhere, and it's going to massively overflow. No problem. We love that. It's going to smell unrecognizable. We could add something to it. That changes it up a little bit. It doesn't have as much of an effect as the big prime multiply. We could square it, right? This helps make it, whatever the result is, it's not likely to be linearly related to the input because it's squared. We can, as we saw with XOR random number generators, we could XOR yourself with your own bits, shift it over. This is surprisingly effective for mangling things. So whatever we do, we're going to mangle, and then return some unrecognizable thing that's strictly based on what you passed in, right? All right. So you're like, cool, I love this. I'm going to go, I forgot what he said. Stack Overflow, give me a noise function. This is what you get on Stack Overflow. Only returns odd numbers. Yes, good. libnoise, I go look up libnoise. It's a nice, really awesome C++ library. What's their noise function? It's the exact same function with a different shift and different constants. When you think about it, noise functions really are just kind of like a very special hash function, right? So a hash function traditionally is I put a paragraph of text in or a file of a bunch of data, and it chews on it, and comes up with a big mysterious number, right? This could be like a CRC or something like that. Really, if we want to just put in an int and get out a mashed up number, we could just think of that as a hash in a sense. All right, there's a bunch of hash numbers we can look at. When Ken Perlin posted his Perlin noise originally, this is the hash function he recommended. So there's a bunch of numbers. That's the numbers 0 to 255, scrambled twice. And then he does a bunch of things where he looks up, just to help you understand what's going on here. This P is this table. So it's a lookup in the table with an offset and a lookup in the table, nested lookups, right? So if this table is 512 bytes, right away we might be having a bunch of L2 cache misses, right? Something like that. All right, so let's look at how these do. There's identity, we said, is the most boring one of all. And Bernstein, libnoise, Stack Overflow, Perlin hash, you can see they all got Ds or Fs pretty much. I'm impressed that Bernstein got lower than identity in terms of quality. That's tough to beat. Perlin hash was the best out of these, but you can see it's painfully slow by comparison to the other ones. All right, we can do better. Aha, right, we have some real hash functions. Why are we monkeying around with this homebrew crap, right? Let's use MD5, let's use SHA1. We just had the first real 128-bit collision of SHA1, I think, like this week. That's what these look like, right? Instead of saying, I have some big file for you to hash, Mr. MD5, you just say, all I got for you is a little integer. Please hash that. And then it does its magic. And these are complex algorithms, right? I think SHA at least came out of the NSA or something. Great. Let's see how they do. So there's a ton of these guys. And if you look at them, if I look at the quality of them, I've kind of mostly-ish sorted them by quality. So you can see there's a bunch of ones that suck. Especially the ones you'd get from libnoise or Stack Overflow and in the searches I've done. There's some other ones. MD5 does great, pretty good at least. SHA does pretty good. CRC does great. And then this murmur thing does pretty great. So there's some interesting ones. When you look at MD5 and SHA1, which are the hash functions I think of when I think of a proper hash function, they're slow, right? Not just like twice as slow, they're 100 times as slow as some of the other hash functions. And for something, if I can already get a pretty darn good quality with something else, why would I use that? And the reason is that MD5 and SHA are like way over-engineered for our simple purposes, right? They're to be cryptographically sound across any body of data of any size. We don't need that. We just need put in and get out something cool. So don't use those. It's way overkill, unless you are actually hashing something for security. So of course, thinking that the world doesn't have enough hash functions, I had to write my own because I'm a masochist. So I took my stab at this and tried a couple different things. I finally this is my third one. And it uses just a combination of, these are prime numbers, so multiplying, bit shifting, etc. After I wrote that, of course, then C++11 came out, and they introduced std hash into the language. That's a little simpler than this. So maybe I should have used that. Let's see how those do. OK, so CPP hash at the bottom, you can see actually does quite well. And they're much faster. They're 3 times faster than any of these other good ones. And then the one I wrote also does very well and is even faster than those. So far, it's pretty good. Great, I'll use my own hash function. But note to self, if you don't want to do that, or you don't want to download my stuff, or trust my code, or whatever, you can probably trust the people who wrote std hash. It's fast, it's good. If you want a good noise function, I would say that's a really good go-to. And out of all the ones that don't suck, pretty much tied for fastest are mine and CPP hash. So of the hash or noise functions that don't suck, these are mostly tied for fastest. And then again, these massive heavy-duty industrial-grade hash functions you really don't need, and you don't need to be spending 200 times as long to get basically the same quality, slightly better results. I use mine because I know what it does, and I absolutely know for sure that on all the platforms it does the same thing. Now, if I go and read the specs, which I haven't bothered to do because I'm lazy, on std hash, maybe it's guaranteed that it will never change the algorithm. I seriously doubt it. Maybe it's guaranteed that it works the same across all platforms, no questions asked. I seriously doubt it. I know mine works that way. So there is some merit to be able to control those things yourself. OK, so we said that we could have seeds in our noise functions, right? And we said not just are they seeds, they're really, really good seeds, where one seed can give you a totally different table of numbers. So really, with a noise function, the seed is quite simple. Instead of setting up some state of a random number generator, we're just involving it in the mangling process. And for me, experimentation has shown, again, if I insert the seed pretty early in the sequence so it gets plenty mangled, but not as the first thing, otherwise it just has the same effect as a position, it ends up giving me very good results. So that's what I use for all my stuff. Of course, if we wanted to use std hash, we could easily seed it as well. The cool thing about hash is that it can hash anything. And so you can just make a hasher that takes both the position and the seed, and it will hash them together. And this actually produces pretty good results, too. All right, so we said we want 2D noise, 3D noise, right, for Perlin noise or anything else, or for determining where those trees are on our landscape. So assuming we have some 1D noise function that has a position and maybe an optional seed, how would we get a 2D position? Well, there's a lot of different ways, and we could write custom different ones that weave in the X and Y and Z positions in different ways. But one of the standard practices that, again, you would find on Stack Overflow or something, is just to take the X coordinate and add it to the Y coordinate that's been multiplied by some massive prime number. And actually, that turns out to be quite good. It's almost impossible to have anything that's recognizable along X versus Y. So that really basically munges the X and Y together into a single one-dimensional position, which we then look up in the table. By the table, I mean the noise function. Same thing with 3D, we could just munge the X and the Y and the Z using different prime numbers, right? And we want them to be orders of magnitude different so that they're not even coming close. So that just any small change in X or Y or Z will have a dramatic effect. OK, so can we build a random number generator out of a noise function? Hell yes, we can. And it's fast, tiny, non-cyclic, thread safe-ish. How tiny, how fast? Depends on that noise function. Let me now build that RNG out of CPP std hash and out of my own hash, and let's see how they compare to the other random number generators like Mersenne Twister. You can see at the bottom here, on the quality scale, we've got 99s for a lot of these. The CPP hash doesn't do quite as well when you ask for numbers in sequence, which is what this is going to do. So it's not quite as statistically good, unfortunately. but it's still pretty good. And if you look at the speeds up here, so this column here is the speed of how many rands I can call per second. Again, the one that I wrote is the fastest out of all these. It's fast to seed, it's fast to rand, and obviously it's fast to get noise from, because that's what it was built off of. And again, with Mersenne Twister, if I did that trick where I seed to jump to a place and then say, give me a value, and then I seed to jump to a place and give me a value to give this random access, that's pathologically slow, right? 1,000 times slower than. Okay, so let's wrap this up. Some tidbits and takeaways. Noise is awesome. That's my takeaway for you. Noise is awesome. Love it. Things that RNG simply can't, or can't do, at least without bending over backwards to pretend it's noise, which it isn't and it's bad at. Coincidentally, noise happens to make better RNGs than the RNGs themselves. And I'm not an academic researcher, but this blows my mind that this seems like such an obvious thing. So I would love, if there are researchers in the room, to contact me afterwards and we can talk more about this, if there's something I'm missing here that's obvious. But I've generated tons and tons and tons of stuff with this, and it does great. Another takeaway, just don't use rand. I know it's convenient, but I mean, for this demo here, I was using GL begin, right? So who am I to say don't use something? But don't use it. It's just bad. It's lousy. You can do so much better and faster, and it would take you 5 minutes to set up a function that smells just like rand, but outperforms it in every way. Honestly, Mersenne Twister, for all it's cooked up to be, isn't the silver bullet that I thought it was, and I got excited about it, and I'm not really anymore. I'm not sure you really need it. My advice in general is keep things small, simple, fast, and flexible. Control them so you know exactly what they do. Noise for the win. So I will put some code, if you're interested in any of this stuff, by maybe the end of next week. All of the slides from all the talks today will be on mathforgameprogrammers.com, including this. I'll just give you a quick look at this. So here's the basic noise function. And then I have a library of simple convenience functions like give me 2D noise, 3D noise, 4D noise, give it to me as floats, give it to me as floats from -1 to 1, whatever, however you want it. I also have that little RNG I built on top of it, which you can seed it, you can change the seed, you can fast forward or rewind it, or you can just tell it, give me a random float, give me a random byte, give me a random direction vector, whatever. Roll random chance. There's a lot of little things like this. You put them in your math libraries. They take nothing to write, they take nothing to call, and you're going to use them all the time. Roll random chance, just you pass in the probability of it returning true, right? Useful. How many times have you written where you roll a number and then you check the thing, right? Why not just check something in the code reads more simply? That is all I have. Thank you guys very much. I think we have time for just a couple questions, if anyone has any. If you do, please come on up to this mic. And please, again, don't forget to fill out your feedback forms. We really appreciate it. And be back in 20 minutes for Mike Acton to talk about the coding game challenge math. Yes?
Hi, I make learning games, so it's really important for me to know the problems that the kids saw during their play experience. And I have them set up so that they're deterministically random, but I'm running into a problem where certain games, the problems that the kids are doing affect outcomes of future problems. And so I came to this talk kind of looking to see if noise could help me to be able to replay their whole levels without having to know exactly what they did at a certain point.
Yeah, and this is your software that you guys control? Yeah, absolutely. If you just, effectively, you just have each puzzle generate itself, or each game, completely independent of the others. And so if they're doing one game and it affects the other outcome of the other, that means typically you have one random number generator and you're pulling numbers off of it, and then you leave it alone and then you just continue pulling numbers off of it. So at the very least, without changing anything, you could reseed the random number generator with a new puzzle and then the past will have no effect. But noise would also be a solution. But in your case, probably just seed more often is my advice. Hey.
Hi. I was wondering if I'm just missing something. Is there any reason not to just use the seed as another dimension in the function?
Yeah, that's a great question. Really, for me, I wanted the seed to have, so I'll say the short answer is no, there's no reason not to. The longer answer is, I like to have the seed that gets mangled more deeply in the noise, whereas for me, I'm a little bit kind of lazily mashing the X, Y, Z together in kind of a simple way, whereas I want the seed to be more deeply involved in the random number generation, so the table feels drastically different, as opposed to just kind of shifted. I haven't done thorough testing with it, but that was my intuition on it.
Okay. Thanks.
Yeah. But I suspect you could do that just fine. In fact, I've used 2D Perlin noise all the time, where I'm striping across it, and if I want a different set, I just stripe across it differently, and that works. Yeah.
Hi. I was wanting to ask you, how do you select like good coprime numbers for spatial hashing, like 2D, 3D, etc.? Because if they're too big, then the overflow it starts like getting influence into the results. So how do you select them?
And you are specifically talking about if I'm combining the X and the Y,
Yeah.
how much should I multiply Y by?
Because I had problems
I had
with
that in a
big
slide,
numbers,
right?
because they overflow and then it's like it starts creating a pattern as well.
Well, if you're multiplying by primes, the overflow actually just throws the extra bits off the end, and actually most of the common random number generators as well rely on the fact that multiplying by primes with overflow stays random and stays interesting. So as long as those are largish prime numbers, my understanding is that it won't be a problem. I think if it's non-prime, then you're forcing it to be odd or even, and if it's small, then it could be recognizable. So in fact, if it doesn't overflow, you should be suspicious that like you might be able to tell where it came from.
Oh.
Does that make sense?
Okay. Yeah.
Like
thanks.
multiply with overflow is really hard to track, I guess, in hindsight.
Okay.
Yeah. Any other questions? All right, thank you guys, and be back here in 20 minutes.